Please join me to welcome Jordan. He is another remote worker. He works at Buffer, and he's better known for his Subjective C blog and as the author of the Spend Stack app. His wife and daughter are here somewhere, seeing him talk for the first time. So that's exciting. There they are. And a fun fact about Jordan is that he's based in Springfield, Missouri, and we're pretty sure he's the only iOS developer in a 100 miles ratio. Today, he's going to talk to us about images, image loading, image caching, the life cycle of an image in iOS, and I think that everyone in this room has been bitten by image bugs. So I think it's going to be very interesting for all of us to see. We're getting everything sorted. Slides. OK, looking good. Jordan, ready? OK, let's clap for Jordan.
All right. Yeah, so the life of an image on iOS. So basically, like the title says, we're going to talk about how rich media gets onto your phone and what it does while it's there, all the way to the moment that it leaves. So before we get started, give you a quick prologue, mention a few things about myself, and tell you how I became so interested in images to begin with, because it didn't really happen by accident. So first, spoiler alert, I am me. I'm Jordan. And like we mentioned, my wife is with me here today. And we also have a really rambunctious 5-year-old. If any of you have kids, they're probably a little bit crazy. And somehow, miraculously, we have an even more rambunctious middle child. And I did say middle, so my youngest daughter is also here. And I'm also very fortunate and lucky to be the full-time developer at Buffer, which I really love. And in addition to the family and the work, like many of you, I also have a side project. So, like most of us, once we get to adulthood, I'm just drowning in free time. And since I have so limited free time, I took a really long time to make my side project. In fact, it took almost 5 years. But this side project I'm really thankful for a lot of reasons, but it's because, in particular, that's how I became so interested in all these images and how they work. So my side project, like I mentioned, is called Spend Stack. And the elevator pitch for it was, my wife and I budget almost exclusively in cash. And so we went to the grocery store, say we brought $200, we wanted to know how much things were costing as we were putting them in our cart. So it sounds like a simple problem, but it's actually a little bit complex because if you have, say, produce, it's priced by weight. And if you have discounts, well, it could be a percentage or it could be a monetary value. Then you can have multiple quantities. And conveniently for us, if you live in the United States, sales tax isn't even applied to any of that until you check out. So it seemed like a problem worth solving, so I sat down to do it. And as the years went on, I got more features in, like iCloud sharing, and then eventually Jansen came to me and said, hey, this is great, this is working, but what would be really nice is if I could put like an image to an item. So that way when you go to the grocery store and inevitably buy the wrong thing the 100th time, now you can just look at the image and know exactly what I'm talking about. So I said, you know what, that sounds good. So stop me if you've heard this before, I stayed up really late, got image support working in it, and when we went to the store and I opened up an item with an image, I noticed this problem. And anytime I opened anything with an image and I tried to scroll really quick, I got this really noticeable hitch. And that's not great, right? Nobody wants that. If I'm spending all these years to make it release anyways, we might as well make it perfect. Famous last words. And if you've seen me on Twitter, I always bark about this notion of a best-in-class app. Like, what do they look like? And that's not it. So, I couldn't live with this. But I couldn't really figure out what was going wrong either. I didn't really know what the problem was. I had a reasonably sized image view. I tried all the tricks like caching the cell height in the table view. The image itself I didn't think was very big. And instruments and time profiler didn't really say much anyways. So, it was kind of like paralysis by analysis. I didn't know what it was, but eventually I knew that if it was going to release, I just had to put the problem on ice and move on. But luckily for me, that was my first WWDC that I went to that year. And I stumbled upon this session called Images and Graphics Best Practices. It was very eye-opening for me because not only did I learn what the problem was and how to fix it, but I learned why I was having that problem to begin with. So after that session and some diving in on my own and tinkering with some code, I kind of came to this point where I understood the life of an image from beginning to end. So if I want to share that with you today, well, what do we need to know about? If we want to understand the life of an image on iOS, what are the things we need to understand? Well, the first one is memory, right? memory is oh so important. It's not just exclusive to images. We all know it pays to take care of memory, but in particular with images, memory doesn't always work the way that you expect it to, especially deep down in the frameworks. So if memory is really important, well, then it stands to reason that we really need to know about photos and images and their relationship with memory. Because there's a lot of things that happen from the moment you choose an image for your app, load it up in the model, and put it on your screen, and things can go wrong. If you don't know where to look, it can be difficult to debug. So with that, let's dive into memory on iOS here for a little bit. And memory on iOS works with a concept called pages. And your app has a ton of these pages, and each one is about 16 kilobytes in size. And what's great about pages is it's really easy to understand, because if you have a notepad in front of you right now and you take out a pencil, you start writing on it, what happens? Well, it fills up, right? And the same thing happens on our iOS apps. As soon as we start allocating and initializing variables or writing the code that we do, when we use it, it starts filling up the pages that our app has available to it. So if you know that your app uses pages, they're about 16 kilobytes in size, well, then you can probably say, well, the number of pages I have times their size is the memory I'm taking. And that's mostly true. But like anything in computer science, it's a little bit more nuanced. And there's three different types of memory that we want to know about. And that's clean, dirty, and compressed. So clean memory is the good memory, if you want to look at it that way. It's just memory you've allocated. And if you've used that ancient language, Objective-C, right, which, by the way, I love Objective-C, use it every day, you've seen this thousands of times. Because what happens when you make stuff, like a UI label? Well, the first message says it right in there. UI label alloc, initialize with frame. So that first message you're sending is allocating memory for you. But apps would be very, very boring if all they did was allocate memory. Eventually, you have to use it, right? So that's when we write to that allocated memory. And at that point, it's dirty memory. And you've heard that phrase probably in computer science a lot, right? Like the cache is dirty, we need to refresh it. Or some people track properties and if they've been written to with a dirty flag. But this last one is a little bit more complicated. And it was added in iOS 7, and that is this notion of compressed memory. Now, compressed memory is memory that's not been accessed in a long time. So iOS can look at that and say, hey, I allocated this for you, you're not really doing anything with it, so I'm going to compress it down. And then compress it down. And then later, when you need it, we can decompress it. So it's kind of dynamic in nature. So if we have those three types of memories, which ones are really going to matter if we need to debug something memory-related later on? And that's going to be your dirty and your compressed memory. Clean memory, you're not really taking any hit on, right? Because it hasn't been written to, it's been allocated, the system can reclaim it if it needs to. But dirty and compressed, you're owning that. So that's your app's footprint. Which brings us to the more important question is, why do we care? No one's going to come to a conference like this, or you're not going to go home to an iOS developers meetup and be like, memory? I don't care about memory, right? I get memory warnings all the time. I see the gauge shoot up in Xcode, JetSam boots my app, whatever. I start it over and move on. That'd be ridiculous. Some of you are looking at me like, I do that. Well, hopefully you won't after this talk. But we all care about memory, right? We all do. And the reason why you should is actually really simple, and it's because everything, after I click it, is better. The entire system works better when you take care of memory. All of iOS is better, right? Your app launches faster, it stays in memory longer, which is really important in our new multiple window world with iPadOS. Whereas on the other side, if you don't, JetSam will kick you out. Or other apps are going to be affected by your memory too, right? It's not just yours. And to illustrate this in the real world, I'm sure some of you have had like a friend or a significant other come up to you and say, hey, my phone's not working, I don't know what's going on, can you check it out? And you're like, yeah, okay, sure. So you open it, unlock it, you go to settings, general, and you go to memory or storage, and they have like a megabyte left for the whole phone to use, right? And that's a problem, and this is why, right? A phone can't work and an operating system can't work if it has no memory, much the same way that you can't drive across the country in a car with no gas. So we need to take memory seriously. So let's look at a real-world application. Made a demo app for the talk, and unlike dub ones, it has nothing to do with peanuts or avocados and peanut butter, but we'll make do. All it is just an image view. That's it. And the one on your left is about 30% larger than the one on your right. So if I was to poll the room and say, which one of these apps takes more memory on account of the image allocations? You'd probably look at it and say, well, the left one, right? It's bigger, more memory. And some of you are probably thinking, well, he's asking this at all, so it's probably a trick question. And you're right, because when it comes to just memory allocations, they're almost identical. And the reason that they're almost identical has almost everything to do with this concept called a buffer. So let's learn a little bit about buffers here. Now, a buffer is a contiguous region of memory. And you can kind of think of it as some memory that's been set aside while you're temporarily storing some data or moving it around. And in our case, we need to know about 3 different types of buffers. And the first one is a data buffer. And this is just a sequence of elements, and they're typically the same size. But the great thing about these data buffers is, in addition to many other types of data, it can hold an image file. And what do image files have? All sorts of useful metadata, right? Is it a ping, a JPEG, TIFF, whatever it is? How big is it? But what it doesn't have is per pixel information. So because of that reason, we have image buffers. And those are a type of data buffer, but in addition to all that other data, it also has per pixel information. So it knows what it should look like at each individual pixel on the screen. It also defines things like color and transparency. And an easy parallel to draw here is if you look at the data buffer and an image buffer, a data buffer says this is the image that I have, and an image buffer will say this is exactly what it looks like. So we'll move on to the last one here, which is a frame buffer. And this one's actually really easy to comprehend because we're all familiar with frame buffers. And for our purposes, all we really need to know is that it holds rendered output. So if we look at this video of these 2 totally random apps that I have no vested interest in or like very much, spin, stack, and buffer, we'll see that the view hierarchy is changing a ton, right? You're scrolling, you're tapping buttons, you're doing all these types of things, just using the app like normal. And what's happening here is UIKit is rendering these changes when the UI window hierarchy occurs, and it's giving it over to the frame buffer. And the display hardware actually looks at this frame buffer on your phone and says, did something change? OK, it did. Let me shift the pixels to reflect that. Because we all know that when we're scrolling something, we're not actually pushing something. We're just shifting the pixels to give us the illusion that that's what we're doing. But this happens really fast, in about 1/60th of a second. And if that sounds familiar, it's because we're always trying to hit this 60 frames per second, right, to get that nice smooth scrolling. And that's what I was failing to do earlier in SpinStack. When I scrolled down to that image, you saw that hitch, and I was dropping a frame. And if you think that's really fast, an iPad with ProMotion will make you cry because that's 1/120th a second, so literally twice as fast. All right, so we know about memory, we know about buffers. Let's kind of draw a parallel to those concepts in code. And what I'm going to show you next is just sample code directly from that app I made. And it's going to look really simple. You've seen this 1,000 times. I have a URL where I have an image. I get that URL. I feed it over to a UI image. And then guess what's next? I create an image view, add it to the view hierarchy, and we're good. But we can see where the buffers are coming into play here. Because really, right now, this is just simple stuff. This just seems like model view controller in action, right? With the image being our model, the image view being the view, and the model gets passed off to the view, and we're all good. But this first part is where we're actually loading in some buffers. And the second part here, where it gets passed off, is where it's rendering. But I said we need per pixel information. So if we started with a data buffer, and we ended with an image buffer, something weird happened in between there, right? It doesn't just magically occur. And data buffers aren't going to give us that per pixel information. So what happened? Well, what happens in between there is actually a really important step, but it's kind of abstracted away from all of us by UIKit. But it's really important to understand. And that process is called decoding. And decoding, like you may have guessed, is how UIKit, or in particular here, UI image, is getting that data buffer and converting it over to an image buffer. So to back on up here, we've got our UI image. We load it in with some type of source, and we get that data buffer. And it's like, OK, I've got a ping. This is my size. But I don't know what I look like. So UI image goes, well, that's not going to be very helpful for us. Let me create an image buffer. So good. We got an image buffer. Now we know that data, and we know what we look like at each individual pixel. But here's where things can go south, because these image buffers can be a lot larger than you may expect them to be. And the reason they can be larger is how UI image decides how much memory it needs to allocate for that image buffer. So we'll bring Baylor back up on the screen here, which I can actually hear back there. So I got you, Baylor. You're up here. You're the star of the show. And this image is 265 kilobytes in size. But really, that's kind of a red herring, because that doesn't really matter. What really matters are its dimensions. And this one is 1718 by 2048. And when we go to get that data buffer, or I'm sorry, the data buffer goes to the image buffer, we can do some back-of-the-napkin math here to see how big this is. So let's assume 4 bytes per pixel. That's a standard sRGB format. If we do that, well, this little tiny image could actually be about 13.42 megabytes. And that's sRGB. If you've got a wide color aware phone, you could double that, right? Because that would be 8 bytes per pixel. So these little tiny images can actually start to balloon up on you and be a little bit larger than you may expect. And remember, this is just a simple demo app with one image. And I don't know a lot of apps that have just one image. So in memory, this gets bad really quick. So again, think in your head about the concepts of memory. Image buffers are dirty memory. It can't be reclaimed by the system. And if it is, it's because you got booted, and that's bad. Plus, the frame buffer, that's happening all the time. So this is staying in memory. Because when you decode, it's CPU intensive no matter which way you look at it. So it would make no sense for the UI image to get that image buffer and then just kick it out, right? So it hangs onto it. Our phones would probably explode in our pockets if they decoded images 60 times a second. So that's where your memory allocations may be coming from for the repeated rendering. So all that to say, my scientific reasoning at the end of this is this can be a real bummer, right? We don't want this. If we have tons of images, we're going to run into problems. And I know what you're probably thinking. I've been an iOS developer for years. I use images all the time. I've never run into this. So what you should do is take a memgraph file, do a screen recording, put it through some CLI tools, and prove it to me. And to you, I say this next slide is for you. So that's exactly what I did. I took a memgraph file of the demo app. And a memgraph file, if you haven't heard of it, is just a file format from Xcode that has a ton of useful information about the way that you're using memory. And then I put it through that CLI tool that comes with Xcode called VMMap. And I get this nice display of my clean, dirty, and compressed memory. So if I look at the top, 69.4, right? That's what my app's using right now. But we really want to know about images. So let's use some regex. Let's look for images. 13.4. And if that sounds familiar to you, it should, because that's what we were guessing earlier. So this tiny image really is taking up 13.4 megabytes of memory just for throwing it into an image view and doing nothing else. So what do we need to do about it? Well, anytime you run into complex problems in development, I find it helps you just kind of take a step back and see where you're at. And where we're at now is we know that UI image makes these image buffers proportional to the dimensions of the image, right? Not really the file size. That's not what matters here. And a lot of times, the image views that we're putting them in are a lot smaller, right? I don't have a 20 by 48 or 17, whatever the size was, image view up there. I've got like a 300 by 400 one. So what would really help is if we could make an image buffer that was just the size that we needed, so there's no wasted work here. And we can do that with a technique that's called downsampling. So let's bring up the rendering pipeline. We know that we're loading, and we're decoding, and we're rendering an image. And we know that decode phase is where things are kind of going wrong on us. So instead, we're going to add 2 extra steps here, shift it around a little bit. And then what we'll do is we'll load in an image source. We'll create what's called this thumbnail object. And then we'll decode that when we want to. And after we've done that, we can wrap it up in a UI image and pass it off to the frame buffer to be rendered. So I'll illustrate what this is going to do for us. There's that picture of Baylor back up. And there's the image view that we were putting it in earlier. And again, remember, we were taking the full memory allocation for that giant image. But now, when we downsample, it's just going to be equal to the image view that we're interested in. So here's some code. This is actually ripped out of SpinStack. We do a very similar thing in Buffer, too. And the first thing you'll know is that we got a few parameters to pass in. And the reason why is we're using a framework called Image.io. And it's a little bit lower level framework, but it's got that thumbnail object for one. And also a lot of high efficiencies for reading and writing a lot of file formats. So it's the perfect tool for the job. But after we get those parameters, we make this dictionary to pass some options. And we're only going to use one here. And what it's saying is, there's an object at this location. You need to know about it, but don't do anything with it yet. And after we've got that, we'll wrap it up and create our image source. And then this next step is where we'll do the bulk of the downsampling work. Now, my mouth's already dry, and I haven't had any water, so there's no way I'm reading these giant, huge key names. But we'll go from top to bottom here. But definitely peek in the documentation if you want the official versions. But starting from the top, the first one saying, when you create this thumbnail, do it from the original image source, right? Not some permutation of it if it exists. And on the second one says, when I request this thumbnail, then decode it. So now we have a little bit more say when the decoding process happens, right? Because it's going to be CPU intensive no matter which way you slice it. Second from the bottom is some transforming work. So we want to rotate and scale according to the image's data. And then finally, this max size comes up, which is, oh, yeah, you heard me, yes, which is really important. I'm doing it. All right, good to go. All right, so max size. So If we didn't pass this max size flag, we're going to end up with an image buffer that's the same size as the image anyway. So we would defeat all the work we've done here. But the max size is super trivial to calculate because it's whichever's bigger, the height or the width of the image view. So then we create our thumbnail, wrap it up in the UI image, and we're set. And if we go back to that demo code we had earlier, the only thing we've changed is we've took out the UI image and we called this downsample method. And depending on how you would use this on your own, you would get that decode and render phase at the point at which you call this. So what did that do? Well, the app would look exactly the same. You wouldn't notice any difference. But if we run that mimgraph file again, and we wait for Pass Jordan to finish his slow typing, we can see if all of that work paid off for us. So we pipe down and just look at the physical memory, and we're at about 57.9, peaking at 62.3. So if we compare the before and after, that's not bad at all, right? We saved almost 12 megabytes just from that one downsample. And that, again, I can't stress this enough. That's one just demo app with one image. So you could save potentially hundreds or thousands of megabytes of memory if you downsample at the right time. So some benefits of that, to recap some downsampling, is when we use Image.io to resize it, it's going to use its streaming API, and we're only going to pay the dirty memory cost of the size that we specify, which, again, is probably going to be the size of some image view that you want to put it in. UI image, it works the opposite, right? You give it an image and it says, cool, how big is it? Great, I'm making that image buffer. Third, Image.io can discard that data buffer too. Remember, the frame buffer, it's repeating and rendering all the time. And then finally, we get to control the decoding point, which can be very important, especially if you get into some collection type situations with table or collection view. So the really important question, now that you kind of know all of this, is when should you do it? And to answer that question, you really need to ask, where are my images coming from in my app? Are they coming from the network, a file directory? Are they in some sort of cache? And if they are, is the image view I'm putting it in smaller than the image? And if you kind of go through that thought process and the answer is yes, then you should definitely downsample. It'd be great. But if you're using asset catalogs, which a lot of people do for their raw image files, you can skip it then, because it already has built-in smarts to kind of handle these buffers for you, so you're not going to see a real gain there. So kind of stepping back, that is the life of an image in iOS. And we now know that if we want to understand the life of an image, we need to know about this load, decode, render lifecycle. And we need to know why decoding takes the memory that it does. And we need to know when it's happening and how to augment it if we do. And if you want to learn a bit more, there's that session I mentioned right at the beginning. It is session 219, and that'll go into detail on this and another type of popular images and apps, which is iconography, which I didn't have time to get to today. And then if clean, dirty, and compressed memory sounds familiar, or you want to learn more about it, that session would be for you. And I am also got a blog post on this if you'd rather read as opposed to watching. I cover both kinds of techniques over iconography and the images. And of course, I'm on Twitter to answer any questions. And if you want to see this happening in an app, again, Buffer and SpinStack both use downsampling, so you can kind of scroll through and see how the images work there. And finally, what I would say to you is definitely stay curious all the time, right? It's so easy in today's kind of social media-driven society. Egos get in the way, and you don't really want to say, I don't know, right? So when I ran into this problem like a year or two ago, I'd use UI image and image view just hundreds of times, and I thought I knew them really well. But it turns out programming has its way of humbling you all the time, and I think that's really fun and interesting, right? It's okay. So there's a lot of power in just saying, I don't know, whether it's on Twitter, Facebook, wherever it is, whenever you're going to a conference like this, because you learn something new, then you get to share it with other people. And with that, that's all I've got. Thanks for listening.